Welcome to the 28th lecture of combinatorics. We were discussing generating functions and we saw several examples how a sequence can be represented by a generating function. To remind you, suppose the sequence is h0, h1, h2, h3 and so on, then the generating function g of x is h0 plus h1 x plus h2 x square plus h3 x cube plus and so on, so hn x raised to n plus. So, we have seen the several situations where a sequence the sequence is such that its generating function has a very nice form. For instance, when hn is just equal to 1, that means the sequence 1 1 1 1 1 1 corresponds to 1 minus 1 by x. G of x will be equal to 1 minus 1 by x, because this expands to 1 plus x square plus and so on, right. Now we will continue with the discussion. We will consider a few more examples. So from that we can get from that 1 by 1 minus x is equal to 1 plus x square plus x cube plus, we can get the generating function of another interesting sequence, namely right, 1 which is equal to 2 raised to 0, 2 that is 2 raised to 1, then 2 raised to 2, 2 raised to 3, this sequence. How will I get it? So I know that 1 minus x equal to 1 plus x square plus x cube plus so on, right. Now what if I write y equal to 2x and then evaluate 1 minus 1 by y, sorry 1 by 1 minus y. So it will be definitely 1 plus y square plus y cube plus and so on, but this y being 2x is equal to 1 plus 2x plus 2x whole square plus 2x whole cube plus so on, right. This is 1 plus 2x plus 2 square into x square plus 2 cube into x cube plus general term will be 2 raised to n x raised to n, right. So the coefficient of x raised to n is 2 to the power n. So the if you had looked at the sequence 1 2 2 square 2 cube 2 raised to n and so on, the corresponding generating function we would have written as 1 plus 2x plus 2 square x square plus 2 cube x cube plus and so on, the coefficient of x raised to n being 2 to the power n, right. So that is exactly what we are getting here, and this is 1 minus 1 by 1 minus y, that is 1 minus 1 by 1 minus 2x, right. So this is what the generating function. So we get the generating function for this sequence is 1 by 1 minus 2x, or we can also write it as 1 minus 2x power minus 1, right. So next we have seen some special cases. We will see a somewhat more general generating function, 1 plus, what about 1 plus x raised to alpha, right. We have already seen this in some earlier class, previous class, that this is alpha choose 0 plus alpha choose 1 x plus alpha choose 2 x square plus alpha choose 3 x cube plus so on. Here alpha is any real number or even complex number, right? So that is what we told. So the so we can define it. So we have seen it when we studied the generalized binomial theorem, right? This is what it is. So what does it say? It says that this sequence for a given real number alpha, say alpha choose 0, alpha choose 1, sorry, alpha choose 1, alpha choose 2, this sequence, right, alpha choose n being the general term, right, and this goes on, has the corresponding generating function 1 plus x raised to alpha. So I told that this is a more general generating function than what we have earlier seen, because so for instance if you one generating function we have earlier seen is the special case when alpha is taken as some positive integer n. This corresponded we saw that this the coefficients were n choose 0, n choose 1, n choose 2, right, up to n choose n, and then zeros in that case. This is the usual binomial theorem, and this 1 by 1 minus x we saw, right, 1 by 1 minus x we saw, that is 1 plus x to the power minus 1. This is actually when I take alpha equal to minus 1, this will become minus 1 to the power 0 plus minus 1 to the power 1, sorry, minus 1 choose 0 plus minus 1 choose 1 x plus minus 1 choose 2 x square plus, so in general the general term will be minus 1 choose n to the power x raised to n, and so on, right. So how does it look like? For instance, this minus 1 to the minus 1 choose n will be minus 1 into, so the next is minus 1 minus 1, right, that is minus 2, then minus 3, so up to it will go to minus n, right, n terms we have to write starting from here 1 to n terms we will write, right, and then this is decreasing. For instance, you see this is the falling factorial, what we have written here is minus 1 n falling, okay. So below it's n factorial, sorry, so this is minus 1, like that only this will go minus 1 minus 2. So that will, yeah, that will make it minus 1 raised to, here we collect all the minus 1's out, so minus 1 to the power n, and we get an n factorial here, and here we get an n factorial below. So this cancels off, we get minus 1 power n. So now sorry, but so this was 1 plus x. Suppose I wanted to consider, see, because earlier we had considered, because I wanted to say that this is a more general form compared to the earlier things we considered. See, 1 minus x is what we considered here, right. So let us say we will consider 1 minus x there, like this. So instead of this we will put a minus here, then what will happen? So then here minus x here, right, minus x whole square here, minus x cube, and the general term will be yeah, sorry, yeah, general term, sorry, here once again. So then if I consider 1 minus x to the power minus 1, what I get is minus 1 choose 0 plus minus 1 choose 1 to the power minus x, right. Here if you want to replace this with a y, you can get the earlier expression and substitute minus x in that. So, rather than going roundabout, we directly write it minus 1 choose 2 minus x square plus minus 1 choose 3 minus x cube and so on. The general term is minus 1 choose n minus x to the power n and so on, right. So, that general term, so this being minus 1 to the choose n minus x to the power n, which is equal to minus 1 choose n minus 1 to the power n into x to the power n, right. So, this happens what this as we have seen is minus 1 to the power n, and this is another minus 1 to the power n. This will become minus 1 to the power 2n, which is always 1, right. So, there will not be any coefficient now. So, we will just get x raised to n. So, going back to this formula, so all these things will go away, it will just be 1 by 1 minus x will just be 1 plus x square plus like this, right. So, that way if you remember this formula, which formula, this general formula, this the general formula we have written here, change it here, right, 1 plus x. So, this formula, this formula if you remember, then everything, all those previous cases can be derived by putting appropriate value for alpha and sometimes taking x equal to minus 1 and so on. So, in that context we should mention that x need not be, so x can be, we can take x as some a times x, then substitute a x equal to y and then use the formula, right, expand the get the expression in terms of y, then y can be substituted by ax. So, wherever y raised to k is come, y raised to n is coming, we will get a to the power n into y to the power n. So, that a to the power n will go to the coefficient, right, merge with the coefficient, it will become part of the coefficient of x to the power n, right. So, now let us take, to illustrate this point, we will take one example. So, we will determine the sequence generated by 1 minus 4x whole power minus half. One minus 4x to the power minus half, this is what we want. Here alpha equal to minus half, and we can substitute say y equal to minus 4x, this is what I was trying to tell, and then say 1 minus y to the power minus half. How will it look like? This will be minus half to the power 0, choose 0 plus minus half choose 1 y plus, so minus general term will be minus half choose n y to the power n and so on. So, that general term minus half choose n y to the power n will become minus half choose n y being minus 4x, right. So, to the power n, right. This will become, so we can expand this, this will be minus half into minus half minus 1 into minus half minus 2 and so on, minus half minus n plus 1, right. We will get a minus 4 to the power n here, and we will have n factorial in the denominator, right. Now, see, we can take a term here, say here this term, this is minus 1 by 2, this is minus half minus 1 and so on. So, what I do is I first take this minuses out, right, from here I take minus out, that what will happen, this will become half plus 1, here I can take half plus 2 and so on, this will become plus minus. What I have done is I have taken out a -1 from each of the terms in the numerator up to here. Okay. So, I got a -1 to the power n from here, because there were n terms here, half, half plus minus half, minus half, minus 1. So, minus half became half now, minus half minus 1 became half plus 1 now, minus half minus 2 became half plus 2 now, and so on, right. So, then this minus n can be merged with, here we have a minus 4 raised to n. So, here if we take this minus, so this is n. So, here 1 minus 1 raised to n can be taken from here, that, and this will become minus 1 raised to 2n, which is equal to 1 always, because 2n is an even number, right. So, this will go away. Now, we have only this part. So, here is a 4n. Now, what we can do is we can, because this is half plus 1 and so on. So, what I do is this 1 I can write as 2 by 2, right. So, that will become 3 by 2. Similarly, here I can write it as 4 by 2, this will become 5 by 2, right. So, similarly, in the end this 2n plus n minus 1, that can be written as 2 into n minus 1 by 2, right. So, how does it help me? Because I have a 2 here from this term, I have half plus 2 by 2, which I can write as 3 by 2, right, and there is a 2 here, and then this is half plus 4 by 2, which I can write as 5 by 2. So, which is here, and this can be written as 2n minus 2, see 2n minus 2 plus 1, that is 2n minus 1 by 2, like this. So, we have a 2 from each term, half in each term, 1 by 2 here, 1 by 2 here, 1 by 2 here. This I can, because I got 2 n such 2's. So, 2 to the power n, which I can cancel with the a 2 to the, this 4 is actually 2 into 2, right. So, that one of the 2 to the power n's will go away, right. So, in the end what I get is 1 into 3 into 5 into up to 2n minus 1 above. The 2 to the power n which was here, right, got cancelled off with one of the 2 to the power n's, and we still have a 2 to the power n's below, and there is an n factorial below, right. This is what is happening, right, 1, 3, 5. So, because every time we were adding an even number, right, next even number is being added, right. Therefore, we get the sequence of odd numbers 1, 3, 5 up to 2n minus 1 in the denominator, and 2 to the power n here, that gets cancelled with one of the 2 to the power n's, a 2 to the power n remains, and we still have n factorial below. So, now what we do is, so we introduce, so here I introduce one more n factorial, and see, to balance it I have to add it above also, right. So, because this thing, if you look, this is 1 into 3 into 5 into 2n minus 1. I would like to introduce a 2, 4, 6, the missing numbers, the even numbers in between, right, till here I will introduce 2n minus 2, and here I want to introduce 2n. So, because 2 to the power n I have, the 2's anyway, the 2's which I need, n 2's I have here, and this n factorial will provide the remaining, because n factorial is 1, 2, 3, 4 up to n, right. So, one of the 2 I take from here and multiply it, I get this 2, and another 2 I take and multiply it, I get this 4, another 2 from here I take and multiply this 3, I get 6, and so on. So, the last 2 will multiply this n, and we will get 2n. So, this entire this thing can be distributed in these gaps here. So, this will become above, what will you get then, 1, 2, 3, 4, 5, 6 up to 2n, that is 2n factorial. Below we have n factorial into n factorial. This is 2n choose n. So, what do we get? The term is 2n choose n, apart from the x to the power n we have. So, the term has become, see here still we have an x to the power n, which because we were just manipulating the coefficient alone. So, the final term will be this into x to the power n, right. So, we see that this minus half choose n into y to the power n, which is equal to minus half choose n minus 4 x to the power n will become 2n choose n into x to the power n. Therefore, this thing 1 minus 4 x to the power minus half expands to 2n choose n x to the power n, right. You can give values for n, and then for instance when it is 0, that will be just 0 choose 0, that is x to the power 0, this is 1 only. When this is 1, that will be 2 choose 1 x 1, and then right, and then when it is 2, that will become 4 choose 2 x square and so on, right. So, in general it is 2n choose n x to the power n. Understood? This is the formula for 1 minus xn. So, this is actually 1 minus 4 x to the power half turns out minus half turns out to be the generating function for the sequence 2n choose n, hn equal to 2n choose n. That means 0 choose 0, right, 2 choose 0 choose 0, which is 1, 2 choose 1, which is 2, and 4 choose 2, and then 6 choose 3, and so on, this sequence. This happens to be the generating function for that sequence, 2n choose n sequence. Now, let us look at some basics. Now that we have mentioned the general form, so these are some special cases, 1 minus r x to the power minus k. So, how will so it is good to right. So, we can always derive it from the general form, namely 1 plus x to the power alpha equal to alpha choose 0 plus alpha choose 1 x plus alpha choose n x raised to n form. So, we can always derive all these things, but so some of these forms are, I mean, they will occur more frequently. Therefore, we just have a look at them. 1 plus r x to the power n, what will happen? Sorry, 1 plus r x to the power minus k, let us say minus k, what will happen? So, this alpha is taking the alpha k minus k is taking the role of alpha, right. So, if I put it here, that will become k choose 0 plus minus k choose 1 x plus minus k choose 2 x square. Sorry, see, as we have mentioned, this is, we should take it as a y or something, and then this will become y, okay, y, and then y square and so on, right. The general term is what? Minus k choose n y to the power n, right. Now, y can be substituted as r x. So, this will become r times x, this will become r square times x square, this will become r raised to n times x raised to n. So, the general term is minus k, yeah, okay, we wanted minus, sorry, I copied it wrongly, I wanted minus r x here, but this is correct. So, let us r x, but yeah, of course, this can be done like this, but the form we wanted was slightly different. We wanted 1 minus r x to the power minus k is what we wanted. So, here alpha is equal to minus k and y is equal to minus r x, right, not r x. This is what we wanted to derive. So, here this is y, right, minus r x is y. Now, this will become minus k choose 0 plus minus k choose 1 into minus r raised into x, right, plus next is minus k choose 2 into minus r square into x square and so on, right, and general term is minus k choose n into minus r raised n into x raised to n. This is what the general term and so on. And what is this? So we can simplify this general term a little bit if you remove this is already simple, minus k choose n minus r raised to n, but what we can do is to convert it to a more familiar form, because minus k choose n into minus r raised to n is what? This is, so this we know can be converted to n. We have learnt this trick of changing the sign, right, change of sign, right. This was equal to this we studied when we studied the binomial coefficients carefully, especially when we studied the generalized binomial coefficients, right. So this is same as this, and this became minus 1 raised to n into r raised to n, right. Sorry, this also needs a this thing minus 1 raised to n, whatever this n, right. So therefore this minus 1 raised to n and this minus 1 raised to n, this minus 1 raised to n is coming from here, this is a negative r, right. So we are getting minus 1 raised to n into r raised to n here. This minus 1 raised to n into minus 1 raised to n will combine to form a minus 1 raised to 2n into n plus k minus 1 choose n plus k minus 1 choose n into r raised to n. This will go away because this is just 1. So we will get n plus k minus 1 choose n r raised to n. This is the general term. General term means this term, this corresponds to the same thing, that is n plus k minus 1 choose n into r raised to n will become the general term here. So therefore what we see is 1 minus rx to the power minus k is same as, yeah, this is the general term, minus n plus k minus 1 choose n into r raised to n into x raised to n. This is the general term, right. We can substitute for the value of n. For instance, if you put n equal to 0 here, this will become k minus 1 choose 0 into r raised to 0 into x raised to 0, right. That means k minus 1 choose 0, which is essentially 1, right. Then put n equal to 1, that will become k minus 1 plus 1, that is k choose 1 into r raised to 1, k choose 1. So that is first term is just 1 only, and the second term will be k choose 1, that is k, right, into r k r. Second, when I put n equal to 2, what will happen? This will become k plus 1 choose 2, right, into r square into x square and so on. This is the sequence which we, sorry, here we have an x. So this is the expansion we will get, right. So we can yeah, so of course we can derive it if you recall the original formula, namely 1 plus x whole power alpha. So just I mean we substituted y equal to minus rx and alpha equal to minus k in that formula and simplified, that's all, right. So but it has a nice form, that's why we did it. And recall that this formula will only yeah, this is equal to 0 to n, you know, this is valid when the mod x is less than 1 by r, because the binomial theorem, generalized binomial theorem, if you remember, had this condition that mod x has to be less than 1 by rx. So this so that means the mod of this rx has to be less than 1, right. That's why this condition is coming, right. So, of course, when we use generating function, we do not have to really worry about this issue of whether it converges or not, because we will be picking up the coefficient and comparing. As long as it converges in a certain range, that will work, right. So, we do not have to worry about whether it really converges for all variables, as long as we are not going to sum it up, right. Most of the time, as you will see, we will just pick up the coefficient of x raised to n and compare, right. That is what we are going to do. So, then now we consider an example which is again familiar. K be an integer, and let the sequence h0, h1, hn be defined by letting hn equal the number of non-negative integral solutions of e1 plus e2 plus ek is equal to n. What about the generating function for this sequence? See, this is a very familiar question. We have already solved this thing. That means we have this equation ek, there are k variables, this is equal to n. What we are interested in is non-negative integer solution for this thing. So, this e1, e2, ek should get values which are integers, but non-negative integers. That means ei has to be greater than equal to 0, right. We have discussed this problem earlier. We know that the answer, the number of such solutions which we can get, different possible assignments of non-negative integers to e1, e2 up to ek, so that they add up to n, is n plus k minus 1 choose n, right. This is the number. But we see that, so now suppose this number of integer solutions is written as for this, and we write hn, right. So, h0 will be the solution, number of solutions when n equals 0, h1 corresponds to the number of solutions when n equal to 1, and h2 corresponds to the number of solutions when n equal to 2, and so on, hn for the general when this is n, and so on. So, there is a sequence like this, and you know that this actually hn value is this, right. This is from our previous knowledge, we haven't solved it here, we have done it before, right. But now we can write the generating function for this thing easily. Why? Because we see that the generating function whose coefficient which is such that its x raised to n has coefficient hn equal to n plus k minus 1 choose n is this. Which one? This, sorry, this one, right, n plus k minus 1. This is 1 minus, yeah, here we have to put r equal to 1, right, because we are only interested in this thing. So, we want r equal to 1 here. So, 1 minus x to the power minus k will be the answer for this thing, right. This here we want a generating function like this, 1 plus h1x plus h2x plus and so on. So, where I am taking h0 is equal to 1, the number of integer solutions 0, that we will fix it as 0 for n equal to 0. In how many ways you can do that? 0, 0, 0, 0, right, that is definitely equal to 1. So, so this generating function where this hn x raised to n, this is what I want to evaluate. What is this gx, right, this is gx, but we know that this hn equal to n plus k minus 1 choose n, right, into x raised to n. Now, you know, if you take r equal to 1, so this earlier formula, previous formula we have derived, that means 1 minus r x whole power minus k, right. This will be, the nth term is becoming as n plus k minus 1 choose n into r raised to n, x raised to n as the general term, right. Now, we do not want r here, put r equal to 1. So, that means the general term will be as we want, right, hn x raised to n, this will become the general term. Now, r has to be 1. So, 1 minus x raised to minus k will give the generating function we are looking for, right. So, 1 minus x to the power minus k, right, 1 by 1 minus x whole power k is the generating function for the sequence we are looking for. So, how did we derive it? We knew the answer before, we knew that the answer for that question, namely the number of non-negative integer solutions for this equation is indeed this n plus k minus 1 choose n. And the previous discussion we have seen a generating function where the coefficient of x raised to n is this. We just had to take r equal to 1, right. So that is how we solved it. Now we can also solve it directly without referring to the earlier calculations, namely, so let us say 1 minus, so let us look at this one. So suppose if we can solve it in the sense that, okay, at least we can establish that this is indeed the generating function for the number of non-negative integer, I mean the sequence of numbers where nth number hn is the number of integer solutions, non-negative integer solutions for that equation E1 plus E2 plus Ek equal to n, right. This is what we are going to do, right. How will you do this? So you write it as this as 1 minus x into 1 by 1 minus x into, so 1 by 1 minus x, right. There are k terms here, right, but we know this one expands to 1 plus x square plus, so the sequence, and this also expands to 1 plus x square plus and so on like that. The kth one also expands to 1 plus x square plus x cube plus and so on, right. Now in this expansion, so for instance if I multiply it out, suppose this is g of x, right. This is so if I have a expansion for this thing, so it will come from this, right, if you expand it out, right. So what would be the coefficient of x raised to n in that, right. So x raised to n can be formed in several different ways from this product. For instance, I can take an x raised to E1 from this, x raised to E1 from this, and I can take another x raised to E2, so a term x raised to E2 from here, and then finally x raised to E3 from the next, and then so x raised to Ek from the last, right. So this can become equal to x raised to n if, so this, when will this become? When E1 plus E2 plus Ek equal to n. That means the selected E1, E2, Ek form a solution for that equation. It is a non-negative integer solutions, I mean assignments, so E1, E2, Ek such that they add up to n, right. So this is what we can do. So but for every possible E1, E2, Ek such that they add up to n, that will correspond to so that will give another x raised to n. So we have to get the coefficient of x raised to n, we have to add up all of them. Suppose some t is the coefficient of x raised to n in the expansion of this thing. That means how many ways we can form n as a sum of E1 plus E2 plus Ek, where each Ei gets non-negative integer values, because in that case, so you can see that is the way we can get it. So more clearly, suppose you take a non-negative integer solution for E1, E2 up to Ek to the equation E1 plus E2 plus Ek equal to n. Then what we can do is we collect for that corresponding solution, we collect x to the power E1 from this first term, x to the power E2 from this term, and x to the power Ek from the last term. Then that will indeed form x raised to n, right, by multiplying out. On the other hand, so any way if you consider a particular way in which we can form x raised to n, that indeed corresponds to a solution of that equation, right. Therefore that indeed counts, the coefficient of x raised to n in this product counts the number of ways we can assign non-negative integer values to E1, E2 up to Ek such that they add up to n, right. So we get directly from this argument that 1 by 1 minus x raised to k is the generating function for the sequence h0, h1, h2, h3 up to hn and so on, where hn is the number of integer solutions for E1 up to ek, where the E1 plus E2 plus ek has to be equal to n for the integer solution for that equation, right. So, yeah, this is one thing, but this argument is very useful because we get how this x raised to n, the coefficient of x raised to n, how is it getting formed, in how many different ways x raised to n can be formed from the product. The first term gives something, second term gives something, and third term gives something, and in various ways they form this x raised to n. Every time an x raised to n is formed, they add up together and then they get it, right. So, that is that's why it's interesting. So, why is it interesting? Because we can put some restrictions on the way we can put take E1, right. So, we have considered such kind of questions when we discussed the inclusion exclusion principle, but we revisit such things in a different way now. For instance, you can look at this question. In the above sequence, let hn be the number of integer solutions of E1 plus E2 plus E3 is equal to n. I am taking k equal to 3 now for simplicity, let k equal to 3. So, E1 plus E2 plus E3 equal to n. And now E1 cannot take any non-negative positive non-negative integer value. It is restricted to be between 0 and 5. That means E1 can only take either 0 or 1 or 2 or 3 or 4 or 5. Only 6 possible values E1 has. Similarly, E2 can take only values 0, 1 or 2. That is, E2 is between 0 and 2. Similarly, E3 can take only values 0, 1, 2, 3 or 4. It is between 0 and 4. Then what is the generating function for this sequence? So, you can see that it is the earlier we had considered the first term as 1 minus x, 1 by 1 minus x, the second term as 1 by 1 minus x, the third term as also 1 by 1 minus, and we had taken k such terms 1 by 1 minus x, right. That is why this 1 by 1 minus x whole power k came, right. That is because this 1 by 1 minus x was equal to 1 plus x square plus all the possible powers of x are there here. That means we are allowing any power of x to be taken for them, including x raised to 0, x raised to 1, x raised to 2, any power of x. But now I do not want it to be like that. I want only either x raised to 0 or x raised to 1 or x raised to 2 or up to x raised to 5 is to be allowed for E1. So, the first term, this first term I will rather substitute with this rather than this infinite sequence, infinite sum. I will have this 1 plus x square plus up to x raised to 5. I will use this here. Similarly, for the second term, instead of allowing all possible non-negative integer values for E2, we are now allowing only x raised to 0 or x raised to 1 or x raised to 2. That is what we told, right. Yeah. So, it has to be between 0 and 2. The third one has to be between 0 and 4, right. So, up to here only we allow, and the third term we only allow 1 plus x square plus so x raised to 4, right. So, this will indeed give the solution for this thing, because if you now you look at the coefficient of x raised to n, right, in this product, what will happen, because this x raised to n can be formed by giving some x raised to e, taking some x raised to E1 from here, some x raised to E2 from this term, and the x raised to E3 from this third term, right. But this is making sure that x raised to that E3 is in between 0 and 5. So, similarly E2 is in between 0 and 2. Here we are making sure that E3 is in between 0 and 4, and if they add up to n, then we will get one more to the coefficient of x raised to n. So, if they do not add up to n, then they are not, it is not contributing the coefficient of x raised to n, right. And anything, any E1, E2, E3 which can add up to n and such that they are satisfying the conditions will come from this also, right. First E1 can be taken from this thing, second E2 can be taken from this thing, and third E2 can be, third E3 can be taken, third that term, third variable E3, whichever value it was given, it can be taken from this and this also, right. So therefore you see that it corresponds to the kind of solutions we look for. But now if you see, this will be a product like this, we can indeed simplify this, because this 1 plus this 1 plus x square plus x raised to 5, we know how to sum it. How much is that? That is 1 minus x raised to 6 by 1 minus x, right. Similarly the next term, this term 1 plus x square is x 1 minus x cube by 1 minus x, and now this one plus x square plus x raised to 4, that is 1 minus x raised to 5 by 1 minus x, right. We can indeed simplify this thing, right. Now so the coefficient of x raised to n in this product will give the number of integer solutions for our problem, with restrictions for E1 and E2 and E3, right. So now let us look at the next question. So we will give some examples for the same problem, but with some more concrete examples. Determine the generating function for the number of n combinations of apples, bananas, oranges and pears, where in each n combination the number of apples is even, the number of bananas is odd, the number of oranges is between 0 and 4, and there is at least one pear. See here it is very clear that we are asking for the number of integer solution for E1 plus E2 plus E3 plus E4 equal to n, with the conditions that E1 has to be the number of we say that the number of apples is even correspond to the number of apples, right, that has to be even, and similarly the number of bananas is odd. So E2 correspond to the number of bananas. So this corresponds to number of apples, right. So this E2 will correspond to number of bananas, right, bananas. So this E1 is to be E1, right, E2 has to be odd, right. These are the conditions, and then one more condition here, the number of oranges is between 0 and 4, and there is at least one pear. That means E3, this is oranges, this corresponds to the oranges. This is, we have E3 is between 0 and 4, and E4, that is pears, right. It is at least 1, that is the condition, that is E4 is greater than or equal to 1, right. So these are the conditions. With this respecting these conditions, how many non-negative integer solutions can be given to this is what we are asking, right. So how will we find it out? Now corresponding to these apples, that namely this E1, we will have one term. So we will add like this, 1 plus x square plus x raised to 4 plus x raised to 6 plus and so on. Why? Because this is x raised to 0, this x square, x fourth, because I am only interested in getting an even number of apples. So I do not allow x raised to 1, x raised to 3 etc., because they are odd powers of x. So I do not want, when I create x raised to n, I do not want the first term in the product to contribute and x to the power t, where t is an odd number, right. So I make sure that all the powers of x here in the first term are indeed even, that is the trick. And second term, which is this correspond to apples, right, and the second term will correspond to bananas, right, they have to be odd, this will correspond to bananas. So that means I cannot put even 1, right, I can only put odd powers of x, x plus x cube plus x raised to 5 plus like that, right. And the third one is easier because we have already seen that, right. Third one says you need oranges, and that should be either in between 0 and 4, right. So, the third term will be 1 plus x square plus x cube plus x raised to 4, right. So, the powers of x are all between 0 and 4 here, right. Now, we are not taking anything more than 4, x raised to 4, x raised to 5 onwards we are not considering. And the last one says we should have at least one pair. That means we cannot take 1, we have to start with x plus x square plus x cube plus so on, right. So, this term will not contribute 1, that means this last term should contribute at least 1 to the power of x, right, when I form x to the power n. Now, when you take the product of this thing, we see that some x to the power e1 plus e2 plus e3 plus e4 will be formed, where this is equal to n. This e1 plus e2 plus e3 plus e4 is equal to n, but this e1 is coming from here, the first term, right. That will definitely is going to be an even number, and this e2 is coming from the second term, that is going to be an odd number as we require, and e3 is in between 0 and 4, and e4 is going to be at least 1 as we want. This is a trick. How many ways you can form it will be easily obtained if we consider the coefficient of n, because in the product we will get the coefficient of x raised to n. When we consider as the number of solutions of this equation which satisfies the required conditions, and to evaluate the coefficient of x raised to n, we can actually consider the closed forms and multiply and see whether we can get something. What will happen? This one now, okay, of course one will ask, how will I get a formula for 1 plus x square plus x raised to 4 plus x raised to 6 and so on. Now, what I suggest is put y equal to x square, then what will happen to this sum? This will become 1 plus y square plus y cube and so on. We know this is actually 1 minus 1 by 1 minus y, and substitute for y now. So, so that is 1 minus 1, this one 1 by 1 minus x square, right. So, the first term is actually this will be actually 1 by 1 minus x square, and similarly this term is what? This term, what I can do is I can take x out from this thing, and this corresponds to the same term. So, this is actually x into 1 plus x square plus x cube plus x square plus x fourth plus and so on, right. You see this x into, other than x, the remaining is the same as this term, right. So, that is the second term is actually x by 1 minus x square, x, instead of 1 we have x because there is a multiplier x here, and this is indeed 1 by 1 minus x square, right. And this is what? This we already know, this is x raised to 5 minus 1 by 1 minus x raised to 5 by 1 minus x, right. And this last term is easy to see. What I do is I take x out from here, so I write it as 1 plus x square plus and so on, right, because this is anyway this second term is actually, so the after x whatever you see is actually 1 by 1 minus x, so you put x also here, right. Thus that will give you x by 1 minus x, right. So, we have this total product as 1 by 1 minus x square into x by 1 minus x square here, right, and here x by 1 minus x and 1 minus x square by 1 minus x, right. So, in the when you multiply all the 4 terms together, what do you get? So, we get x square into 1 minus x raised to 5 in the numerator, x square into 1 minus x raised to 5 in the numerator, and in the denominator we have 1 minus x square whole square into 1 minus x from 1 minus x whole square. Now, if you want to find the coefficient of x raised to n in this thing, how will I go about doing this? I can, because this is the usually if you want to get the final answer, we have to really find out the coefficient of this kind of an expression, right, coefficient of x raised to n in this kind of expression. For instance, I can try like this. I will rewrite this as x raised to 2 minus x raised to 7 divided by 1 minus x square whole square into 1 minus x whole square, right. Now this will be two different sequences. So one is x square by 1 minus x square whole square into 1 minus x whole square, and minus x raised to 7 by the same thing, 1 minus x square whole square into 1 minus x whole square. Now I can take, so the when I am interested in the coefficient of x raised to n, I can get the coefficient of x raised to n in the expansion of this, and I can get the coefficient of x raised to n in the expansion of this portion, and then take the difference, right, this coefficient minus this coefficient, right. So I can concentrate on say one of them, say let us say, because if I can do this thing, I can do this also, right. So here you see this is x square into something, x square into 1 by 1 minus x square whole square into 1 minus x whole square. Suppose I find the coefficient of x raised to n minus 2 in the expansion of this, then that will correspond to the coefficient of x raised to n in the expansion of this thing, right, because x square anyway is multiplying each term there. So if you are looking for the power of x raised to n, we should rather look for the power of x raised to n minus 2 in the remaining. I discard this and look for x raised to n minus 2, the power coefficient of x raised to n minus 2 in this thing, and this. So in this case what will you do? So you should look for the power of x raised to n minus 7, because x raised to 7 is multiplying every term. So if you are looking for x raised to n, we should actually look for the coefficient of x raised to n minus 7 in the coefficient of this stuff, the remaining, discarding x raised to 7, the remaining is 1 by 1 minus x square whole square into 1 minus x whole square, right. So we will be interested in the power of some x raised to n dash. So either it is x raised to n minus 2 or x raised to n minus 7 or whatever, 1 minus x square, this thing, right. So here if this is, suppose if I take a of x, sorry, say f of x is equal to 1 minus x square whole square and g of x is equal to 1 minus x whole square. This, for both of this thing I know how to expand using the formula 1 plus x raised to alpha, right. So and now I am interested in the coefficient of x raised to n in h of x, which is f of x into g of x, right. Now we see that the if h of x is equal to f of x into g of x, and say if h of x is equal to c0 plus c1x plus say cn x raised to n, then cn will be equal to a0 into bn plus, so I will discuss this because the time is over, I will discuss in the next class.